All right. Hello, welcome everybody to our first CU Prime talk of the semester. My name is Tyler. If you haven't met me, I'm a grad student in my 6th year in the physics department. So welcome to CU Prime. We are a group devoted to building community in the physics department and beyond. And so one of the things that we do is host a talk series where grad students, maybe even undergrad researchers or postdoc researchers get the chance to present on their research and on their career trajectories in a jargon-free way. And so the hope is that you all will get something out of these talks. If at any point through the talk you have a question, then please interrupt, raise your hand, and we'll be happy to answer that question. And then throughout the talk, we'll also have periods of discussion where you get a chance to turn to your neighbor and discuss some of the concepts that we discuss. So we hope that it is an enlightening talk. I'll also mention we usually have pizza. I'm very sorry, it will be here, but probably not for another 5 or 10 minutes. And so the first time that we have a break in the talk, then hopefully the pizza will be there by then. We can go up and get it as well at that time. But for now, we'll have to be pizzaless for the next 5 or 10 minutes. Okay, without further ado, let's go ahead and get started. Welcome everyone, come on, have a seat. And yeah, one other thing I'll mention, we are also live streaming this. So if anybody is joining on YouTube, then welcome. And if you have any questions, feel free to put those in the chat and we'll be happy to accommodate those as well. So our speaker for today is Sara Moore, who is going to tell us about her research in the engineering department, but also in the physics department and how those two things combine together in a really cool way. So let's all give a hand for Sara.
All right, hello everybody. I'm Sara Moore, like Tyler just said, and the name of my talk is Capers and Tapers. It came to my attention recently that not everyone knew what I meant when I said capers. Some people thought I meant the little green ball. Some people didn't know what I meant at all. What I meant was antics with tapers. So I'm gonna go ahead and start the talk with who I am. So I'm California born and raised. I went to the University of Minnesota from 2018 to 2022. Where I got degrees in math and physics. I also like climbing and baking bread. And right now I'm a 2nd year grad student here at CU, like Tyler said, in a joint lab between the engineering department and the physics department. So we're gonna start with my journey through physics. I always have liked math. I always knew I liked math. And so I started out my career at the University of Minnesota as a mathematics major. And as part of that, I had to take the first 3 physics courses for my math degree. And I really liked them, but I was really scared to major in physics. I think there's a lot of this sort of stigma around what majoring in physics is. I also was told for a lot of my life that I was going to hate physics, and also that women's brains didn't work great for thinking in 3D, so I wouldn't be able to do it. That is wrong. But it really scared me off of majoring in physics. And so I didn't declare a physics major until the very end of my first semester of my 3rd year of undergrad. It took me a really long time to say, now I can do this. So I'm just going to kind of walk you through what my research journey looks like. So I started research in a panic. I started research as a 2nd year in undergrad. I was going, I'm a math major. I'm never going to get a job. I better start doing research. I hear jobs like that. And so I contacted a bunch of different grad students and I started doing a reading project on analytic number theory. And I didn't like it. Math is really fun. Doing math is really fun. I found doing math research not very interesting and really terrible. I was doing something called lattice models for number theory. Don't ask me anything about them, please. I didn't know when I was in a 2nd year. I don't know now. And I hopefully will never, ever know. And so I stopped that reading project. And around the time I hit my 3rd year, I was thinking, well, maybe I should declare a physics major. And one of the things that kind of pushed me over the edge was my school offered a junior research project. And it was a project that you took as a class. It was a semester-long project. You worked with a partner, you had a mentor. Me and my mentor talked about surface plasmon resonance dependence on film thickness. So a plasmon is just a collective oscillation of electrons, and a surface plasmon resonance is that oscillation happening at the surface. And we wondered if the band you saw in the reflection off of these metal samples would change if you had different thicknesses of films. Ultimately, we didn't get any data. It was a horrible project and we didn't get very much done. But unlike my math research project, I actually kind of enjoyed this one. I thought it was really fun to work in the lab. I really liked talking about physics. I really liked playing with the equipment. And so even though it was similar to my math project in that I don't know how much I got out of it, I ended up really liking it. And around the same time, I started working on the University of Minnesota had a collaboration with Fermilab, where we are constructing and testing panels that are going to go into Fermilab's muon to electron conversion experiment, trying to see if the standard model of particle physics holds. So these are what those panels looks like. That's mostly what I did. And it wasn't and that brings me to my project. So the goal of my entire project is to create a tunable Raman laser with a liquid microresonator. And that's a lot of complicated words, but we're going to break it down and we're going to go through them one by one. So starting off with kind of the big idea behind my project, we want a really small controllable laser. Why? Controllable lasers have many applications, including characterizing materials, optical communications. Why do we want it small? Some applications require compact sources, sensing, quantum technology. So there's going to be a lot of different applications in the real world of really small lasers. You might be asking me, how small is small? If you take a standard Nalgene bottle, you can fit, now these lasers are in liquids, so they're droplets. You could fit about 30 million lasers into a standard Nalgene. So pretty small. And so I'm going to start by talking about lasers, but first I want you all to talk about lasers. So discuss with your neighbor, what do you know about lasers? I'll give you like 3 to 5 minutes. All right, it sounds like talk's kind of dying down. Does people want to shout out a couple things they know about lasers?
Can't shine out planes.
Yeah, don't shine them at planes. Excellent. Excellent. They're light. Yeah, that's great. Is that the only things we know about lasers? Excited atoms and stuff. Yeah, for sure. All right, does anyone have anything else? Yeah, Maeve.
So like working with like the geometric optics is something in the box. So that's like a line and they like years,
Yeah, lasers can be a total pain in the butt. Tyler, should I pause here so people get pizza or keep going? Okay. Yeah, I've got a couple more. So yeah, that's a lot of great answers. Lasers make light. Lasers involve excited atoms in some sort of way, which brings me to my first slide about light and excited atoms. So excellent introduction. So light is emitted when atoms go from an excited state to a non-excited state. So atoms have different places where their electrons can hang out. And so any place that's farther from the center of the atom is going to have more energy. It's going to be like me holding a ball at the top of a building. It's going to have more energy and it has more potential to go fast at the bottom than if I was holding it right next to the bottom of, say, this tower. And electrons that fall from an excited state to a less excited state emit a photon so that you can have a balance of energy. So they emit a photon, which is a small packet of light. So you have an atom in an excited state dropping to an unexcited state, and it'll emit a bit of light. And that is called spontaneous emission. And sometimes when that photon that's emitted interacts with another photon, we get what's called stimulated emission. And so you can see what that looks like right here. So an atom is excited, that electron drops down, and it interacts with this incoming photon. And then both photons leave, and they have the same direction and they have the same phase. So they're going in the same direction, which is a really cool thing that we can use in lasers. And that's actually what the S and the E stands for in laser. Okay, so now we know that atoms can emit light. How do we use that to make a laser? So there's a couple of different things. First, you need a place to get the atoms. So you need what's called a lasing medium or a gain medium. Gain is just a fancy word for the ratio of the output power to the ratio to the input power. And that input power comes from what's called our pump source. We need something to get those electrons up to the excited state. And so our pump source can be a lot of different things. Sometimes it's just a voltage or electricity. Sometimes it's another laser. Okay, so now we have a block of atoms that are all excited. They're emitting light. Light's going everywhere. But how do we get that light to go in a line? Because one of the things, and one of the reasons you can't shine lasers at airplanes is it's going in a line and it'll keep going in that line for a really long time. And so what we do is we add mirrors to either side of this laser to kind of confine the light. And so what happens is, let's say we have a laser that's coming over this way, so that'd be to your right. So coming over to the right, it's going to hit that mirror and it's going to bounce back. And on its way back, if you remember what I just said about stimulated emission, it's probably going to interact with some other photons and it'll get those photons going the same direction as it in the stimulated emission portion of it. So let's say it's going back and it picks up 2 other photons and it on its way back over to that other mirror. Then those 3 photons will turn around, they'll bounce off the mirror and they'll come back towards me. And let's say each of those photons picks up another 2 photons. And so eventually, if you continue this process for a while, you get all of your light bouncing back and forth between those mirrors. And then what we can do is we can make one of these mirrors either partially reflective or we can put a little hole in it that lets all of that light that's been bouncing back and forth out. And it creates just a stream of light. And so there are a couple constraints on how cool lasers are. And one of those constraints is that in most lasers, only certain wavelengths are allowed because of the fixed or the set energy levels that we have in different atoms. So different atoms have different places where the electrons can be, and those are fixed. They won't change. And so you only can get certain photons because you only can drop certain distances. And this is bad news for us because we want a smoothly tunable laser. And so over here, I don't know if, yeah, my mouse does show up on the screen. So you can see these are kind of the allowed drop levels we can have. So this is how much that electron can drop. And then there's also another issue, which is sometimes there's only certain portions of the medium that are going to allow for lasing. And so we get different peaks like this in a laser. Yes, Tyler. The axes? I don't know, Tyler. Yeah, the x-axis would be frequency probably. Yeah. And so one way we get around that is by using something called Raman lasing. And so these are not electronic transition, but they're vibrational transitions. Instead of taking an electron up and bringing it back down, we're putting a photon in, and then that photon will vibrate our atom. And there's certain ways that the atom likes to vibrate. And all of the remaining light will come out. So here you can see, instead of just going up and back down, we'll go up and then we'll go down, not all the way. And that extra bit of energy right there goes into making the atom vibrate. And this is good because this means it's flexible, both what we can put in and what we can get out. And so essentially we can have any wavelength come out if we either have an appropriate input or if we have an appropriate cavity size. And I'll explain what I mean by cavity size in a second. And this is the second. So you can get any wavelength by controlling the cavity size. And what I mean by that is in a cavity, there's something that's called a standing wave. So you can have photons or light waves traveling back and forth in a cavity, and they'll add together and interfere. So you're always going to get this red wave, which is called a standing wave. And you can see it's fixed on both ends, kind of like how a guitar string is fixed on both ends. So there's only certain wavelengths that are going to fit in that portion. And so if we change the length of our laser by a little bit, we can get different standing waves. And now just briefly, I'm going to hop into liquids, we're making our laser out of a liquid, which means that our gain medium is a liquid. And we're doing this because liquids like glycerol and water have really large Raman gain bandwidths. And so this is a large portion of wavelengths that are good at giving us Raman back. And then the last word in this is microresonators. So hopefully now we all have a sense of what a laser cavity is. But what if they were really small? What if they were on the scale of micrometers? We might call them microcavities or microresonators. And I threw up this picture up here because it has a lot of different microresonators on it. So you can see what through the years people have tried out. So this one's a sphere, this one's a torus, we've got a ring, we've got a racetrack going on. This one, I don't know how this works. This is a post or a pillar. And so now you might be saying, whoa, 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 I thought laser cavities looked like this. I thought laser cavities were kind of a rectangle. Some of those were circles. Some of those were discs or spheres. How do I get a laser happening in a circle or a sphere? And that leads to my next question. So discuss with your neighbor, and while you're discussing, maybe go get some pizza. How could we get modes happening in lasers that are circles? All right. So it sounds like people have quieted down again. Does anyone have any ideas on how we could get modes happening in lasers that are circles?
Circular lasers.
Absolutely. So what we do in lasers that are circles is we have something that's called whispering gallery modes. Whispering gallery modes were discovered in St. Paul's Cathedral in London. When people would stand on opposite ends of this cathedral, they could hear each other perfectly, even if they were whispering, which is why they're called whispering modes. And so what was happening here is the sound waves were moving around and they were bouncing off the edges of the cathedral in a circle. And so we can apply the same principle, but in a droplet resonator. So at a scale roughly 200,000 times smaller than the cathedral they were originally discovered in. And another thing is, so when we have the modes bouncing around the outside, we want to make sure that there's very little loss. So we have liquid droplets that are lasers. These liquid droplets are supporting Raman lasing. Smoothness is another big reason to use a liquid droplet. So they have what's called a high quality factor or a high Q factor, and that means they're really, really smooth. So you can see in this graphic up here, the smoothness of a couple of different things. So if you just mill something, like if you go down to the machine shop and start milling it, that's going to be not super smooth. But you can move along this graphic and you can see polishing would get you smoother than milling. The Hubble lens is in there in between polishing and the commercial lenses that we typically use in optics labs, but even smoother than all of those things, even smoother than the Hubble lens, even smoother than the lenses we typically use in optics labs are liquid droplets. And so by using them as our lasing medium, we get a really high quality factor and really low losses. And so just kind of bringing you back to our goal, which is creating a tunable Raman laser with a liquid microresonator. We've covered Raman, we've covered laser, we've covered liquid, we've covered microresonator. So we really only have one word left, and that's tunable. So like I said before, if you have Raman lasing, there's two ways to get any wavelength out of this. And what we want is we want a laser that can lase at a continuous scale of wavelengths. And so we either can correct the pump wavelength, so correct the wavelength that's coming in, or we can change the cavity size to get different modes. And correcting the pump wavelength would mean we needed another tunable laser, and so on and so forth. So we're not going to go that route. And so we're going to change the cavity size. We're going to change the cavity size with something called electrowetting. And so I have another discuss with your neighbor. I want you to think about what makes liquid droplets the shape that they are and how we could change the shape of liquid droplets. So I'll let you guys discuss for a minute. All righty. So can anyone tell me what they think makes droplets the shape that they are, or how we could change the size or shape of a droplet? Surface tension. Awesome. Does anyone have any ideas on how we could change shape of a droplet? What was that?
Add a surfactant.
Add a surfactant. We could add something for sure. So Sarah, you're absolutely right. surface tension is what keeps droplets the shape that they are. So liquids form these droplets because of surface tension, and that surface tension is caused by attractive forces between the molecules in the liquid. And if we apply voltage or electricity to this droplet, we can build up negative charges on the surface, which will weaken those forces between the molecules, and the water is going to change shape. And so this is really cool because it is easily reversible. Unlike if we had a cavity that had mirrors on both ends and we had to move them little by little, that's not super easily reversible. This is easily reversible because you can just stop applying the voltage and they'll go back to normal. And then also this is really, really fast. So less than a millisecond for response times. So we can change the shape of this droplet really quickly and really reversibly. And so what this does is this changes the circumference of the droplet. So we talked before about how changing the length of a cavity could change the modes that you have. Changing the circumference of a cavity also changes the modes that you have because it's a different length around. So your cavity is a different length. And so this is kind of a picture of what those modes look like going around the outside of a droplet in those whispering gallery modes. So let's bring it all together. Lasers have modes. We can create modes in microresonators. We can make microresonators out of liquids. We can change what modes we have with electrowetting. And after all of that, we can get a tunable laser out. That's a lot of steps. So this is what our experiment actually is going to look like. So here you have, underneath you have a waveguide. So that's essentially going to carry in your pump wavelength. You have a droplet that we're going to control with electrowetting, and that voltage comes from electrodes that are on these sidewalls that are holding this droplet up. And then you can get modes going around the circumference of this droplet. And so that's really cool, but what am I actually doing in lab? So some of it is burning my fingers and trying not to look at lasers. But this is also a big project. We need to make chips that actually look like that picture and that work. And so there's a lot of preliminary steps. And so the first step is I'm trying to get Raman lasing in a droplet with an easier setup and no electrowetting. Yes, me.
I'm wondering roughly how big is water droplet and like the whole like setup, like
yeah, so the droplet is about, it's a radius of about 100 microns. Yeah. And so I'm doing this easier setup that involves a tapered fiber to get the pump wavelength in instead of a waveguide, and it involves a silicon oil droplet instead of water or glycerol or something else. So I'm not worried about electrowetting. I'm just worried about getting Raman out. And so day to day in lab, I'm making tapers, I'm making little microresonators. And so day to day, I am modeling what we want the setup of the real deal to work like. So that means reading lots of papers, that means learning different softwares, that means modeling those different things. And then I'm also modeling this other experiment here. So making tapers, making microresonators. And what this is right here, and I don't think you can see it on this screen, but there's a little fiber that runs across here. These two are motors, and that's a heater in the middle. And so I take a regular fiber and I just pull on both ends while I'm heating it up. And ideally, it makes it thin enough that I can get light out of it and into a droplet. And that's also where the finger burning happens. And so now getting into the nitty gritty, what does my day-to-day really look like? So usually I get in at 9, fire up the laser, emails, coffee. I'll try to taper a fiber. Usually that doesn't work, so I'll troubleshoot. And then I'll try again, and then I'll troubleshoot some more. I'll stop troubleshooting, eat lunch, maybe read some papers, maybe go to class if I feel like it. And then I'll probably troubleshoot a little more, and then I'll go home. And that's kind of what the day-to-day looks like. It's a lot of things breaking and fixing them. And that's the end of my talk. Yeah.
Great. So we have plenty of time for questions. We'll probably take about 10 or 15 minutes to have discussion and questions. So start thinking of your questions. In the meantime, I'll tell you about a few things CU Prime is doing. So if you would like to fill out the survey, let us know how this talk is. Let us know how you think these talks should go in general, or what you would like to see in the future. And if you're interested in helping out with the talks, we always need more people to help set up and make flyers and all of that cool stuff. So if that's so, then feel free to talk to me or reach out on this email at talks@cuprime.org, and we'll be happy to have more people helping out. One other thing I'll mention, CU Prime is starting a weekly coffee snack hour on Fridays. So if you're free on Fridays between 10:30 and 11:30, then we are going to have time for a study break, or maybe a study session if you so choose, or just a time to hang out, meet your classmates. And that will be in the student group office, which is in Duane 135A. If you've been to that room, it is across the hall from the TA office on the first floor. It's also across the hall from those glass study rooms with the glass walls. So that'll be again Friday at 10:30 to 11:30, and every Friday after that till the end of the semester. I hope to see you all there, just so you can stop in and grab some cookies or something. But yeah, let's get back to capers and tapers and whatnot. What questions do people have?
Why are you using the oil drop? Like, why is that easier than starting?
Yeah, that's a great question. So it's actually oil that's coating a silicon microresonator. So you can make the microresonator out of glass first and then cover it in oil. And so that way you're still coupling into a liquid, but it's a lot easier. You don't have to use like a droplet dispenser. You can essentially just light the end of a silica taper on fire and then put it in some oil and you're good to go.
What is the goal of using the easier setup before you mount the setup?
I think the goal is to get used to a lot of the different ideas in this. So to just observe Raman and see what that looks like.
Is that supposed to be tunable in some way?
The one I'm currently working on, no, it's not supposed to be tunable.
Do you have a predicted range for tunability? Like how much you can stretch the water droplet?
I don't know that off the top of my head, but I believe there is a range.
Do you expect the motion of the droplet to affect how much light you can get out of the droplet?
I don't think so. The settling time after we apply the voltage is pretty quick. So it'll change shape really quickly and then it'll stay that shape. Yeah, like less than a millisecond.
What are the like intensities and frequencies?
Right now, I can speak to what I'm doing right now. I don't know about what it's going to look like in the end. Right now, I'm working with probably like just like a milliwatt of power, and then the frequency is 780 nanometers.
Okay, so the way that it works, where you have that like bouncing around like inside of a water droplet.
Yeah.
I get that it stays in there with total internal reflection, but how do you actually get it back?
Yeah, so I can speak to what I'm doing right now. Essentially what happens is this taper is so thin that the light is coming out evanescently. So the light is just spontaneously coming out. So it'll couple into this droplet and then it'll couple back. There's kind of an exchange happening right where this taper is. And you can see Raman on both sides. Yeah.
Is it something about the droplet being in contact with the fiber that's causing that coupling? And that's why it's not just like coming out everywhere from the droplet.
Yeah, it's how close the fiber is. You actually have to get it close, like a very specific distance away, so that you can, it's called like the effective refractive index, and you need to match those things by having the taper be a certain diameter. Yeah.
With external forces on the droplet, such as gravity or the sun is accelerating, would that produce any measurable shift of that frequency?
Yes, most of these droplets aren't super affected by gravity because on the scale we're at, the surface tension is a much larger force than gravity. But yeah, if you had it on like a shake table or something, the vibrations probably would affect it. Yeah.
Sort of more in-depth question. So could be nonsense. When doing theory for this, are you able to you got to do anything special look at semi classical approaches or or are you just doing full plastic or plastic thermodynamics it's have the tapering it's really good. So
Mhm.
wondering you got to how it's being treated through walls.
It is mostly being treated classically.
Earlier you said that this lab is joined between the physics and engineering department.
Mhm.
Why is that?
Why is that? That's just where my professor works. She has a dual appointment in the electrical engineering department and the physics department. Most of her students are physics grad students, but all of the classes she teaches are in the electrical engineering building.
So I guess I have two questions. One is just to follow up on that, how was the transition? Is it hard to do that as a grad student switching to a different department, or is that commonplace? And then my second question was what can we do with this? Because I usually think about the handheld lasers you have for presentations or something. But these it seems like you're putting them on chips. So what sort of things, what are the applications of lasers of this?
Yeah, so I'll take your first question first. Most of Juliet's students are physics students. I believe she only has one electrical engineering student. So the transition over there was pretty easy. I also really liked that there's a lot more applications to this kind of work. And then the second question was, what are some applications of these chip scale lasers? And so there's a ton. There's applications in communications, sensing, different quantum technologies like optical clocks. Does that answer your question?
What does communications mean?
So that's a good question. I think mostly just communicating via optical fibers, and I don't really know how that particular application works. Hey, Greg.
What do you detest the most about grad school?
That's a good question, Greg. I wasn't anticipating that. He said, what do you detest most about grad school? I'd say homework, not taking the homework.
Have you considered the applied physics track?
I am part of one of the applied physics tracks. So yes, I have considered. And the answer was yes.
Can you talk a little bit more about how your project fits into your lab generally and how that
Yeah.
works?
So my lab has a couple of different focuses, and one of the subgroups of my lab is electrowetting. So that's anything where we're taking a liquid and we're changing the shape of it. We use electrowetting to do a lot of different things. So my project uses it for lasers, but there's a lot of other projects where instead of using it as a laser, you can send light through it and use it as a lens, like a tunable lens. Darwin actually works on some of those other projects. I think right now we're thinking about using it as a hydrophone, so to detect different sound waves. So basically anything that has to do with droplets or to do with liquids is one of the subgroups of Juliet's lab.
Any last questions? If you guys have anything else, feel free to stick around for a bit. Feel free to come up and talk to Sarah. But otherwise, let's thank Sarah one more time.